OCR Statistics, Discrete Random Variables 2, Binomial and Poisson Distributions. This is the final video in this section, 2.6, and it's on the mean and variance of the Poisson distribution. The first thing that we're going to do is have a look at the Poisson distribution in GeoGebra again. Notice here I've set the parameter to be equal to 1. Over here you can see that you get the mean and the standard deviation as well, and they're both 1. Now this distribution looks a little bit like a histogram, which it shouldn't really, because we should only be able to get values of 5, 4, 3 and so on. We shouldn't be able to get 0.5 or 1.5. So if you go up to the top here and click on this button, you'll see it changes to this, where each of the parts are just lines. Okay? Which means obviously we can just have 4 or 3. Okay, so this was what it should look like when we're dealing with Poisson. Now what we're going to do is we're going to change the value of the parameter, and I'd like you to watch the mean and the standard deviation values over here and see if you spot a pattern. So first of all, I'm going to change it to 4. So you'll see the distribution changes, and over here we've now got a mean of 4 and a standard deviation of 2. So it's looking like the parameter and the mean are the same value. But what's happening with the standard deviation? Well, let's try 9. Okay, so now the standard deviation has gone to 3. Okay, you can probably tell what's happening here. And then let's try 16. Okay, so as expected, you probably spot that the mean is the same as the parameter, and the standard deviation is the square root of it, which means obviously that the variance will also be the same. Okay, so what we've just discovered from GeoGebra is that when we are modelling using the Poisson distribution with parameter lambda, the expected value, or the mean, is also the same, and the variance is also lambda. And this is an important property of the Poisson distribution, and we can assume it as well. It's very useful when checking to see if observed frequencies of a random variable will fit a Poisson model. And you are given this in your formula booklet as well. So there's a table in your formula booklet, and you'll see in the Poisson row that you're told that the expected value is lambda and the variance is lambda as well. So as long as you know to look, it's there. Now let's consider an example. In this case, we have a firm that has investigated the number of employees suffering injuries whilst at work. And here we have the results for a 52-week period, so essentially a year. So we do have this section here, which is greater than or equal to 4, which would be difficult to enter into a calculator, but thankfully this is 0, so we can kind of disregard this, so don't worry about it. So the first part of the question is asking us to give reasons why we might expect this distribution to approximate a Poisson distribution. So you should recall that previously we said in order to use a Poisson distribution, we must assume that events occur singly, one at a time. And I think we can reasonably assume that injuries occur one at a time in this case. Also that they occur independently of one another and at a uniform average rate. So we're going to assume that these things happen and follow a Poisson model. The second part of the question is asking us to evaluate the mean and the variance of the data to explain why this gives further evidence in favour of a Poisson distribution. So we could reasonably just enter in this part of the table into our calculators, and that will give us our mean and variance. But I'm also going to show you by hand. So in this case, we know that n is equal to 52 because there was clearly 52 weeks in the year that we were dealing with. Also, the sum of the x values. Okay, well we've got one injury here 17 times, 2, 3 times, and so on. So we multiply these and add them together, we get 26. We can also get the sum of x squared in a similar way, and that turns out to be 38. This will give me a mean of 26 divided by 52, which is 0.5. And our variance, I'm going to use the formula the sum of x squared minus n times the mean squared, and that's all over n minus 1 because we're dealing with a sample. So if I input all of these values, I end up with 0.490. So here is this written out neatly again. And notice that the mean is 0.5 and the variance is 0.49. So these are very close to each other. We can say that the mean is approximately equal to the variance, and therefore this is another reason why the Poisson distribution is a good model in this case. This was the final video 2.6, mean and variance of the Poisson distribution.